In this video, we're going to take a first look at a simple quantitative risk assessment. If you've not viewed the qualitative risk assessment video, you might want to do that because it provides some useful background for the model that we're looking at here. In fact, this is the model that the qualitative risk assessment video ended with. We've defined risk earlier using a conceptual model that says risk is a probability times a consequence. If you take a look at the bottom left, you'll see we have two tabs in this model, a probability and a consequence tab. I'm going to focus primarily on the probability tab just because I don't want to overwhelm you with too much information when we're just trying to get a sense of how these models work. The model we're going to be talking about is examining the risk of an aquatic nuisance species in one watershed becoming established in another watershed. In order for that to happen, there are 5 specific events that have to occur. And these are the events that are shown in the event tree that we're looking at. This event tree was built using the Precision Tree software. And here you see the Precision Tree tab. We also use the at-risk software, shown here on the at-risk tab. These are add-ins to Excel software. A copy of this software is made available to anyone who's going to be taking the course or who buys the textbook, and you will learn how to use this software in the graduate certificate program. So in this particular video, I'm not teaching the software so much as demonstrating some of the ways that it can be used to help us do quantitative risk assessment. So back to our story. In order for the aquatic nuisance species to become established, first a pathway must exist. Does a pathway exist, yes or no? And we have a probability here. There's a 100% probability that it does exist because we can in fact see it. If a pathway exists, then we would like to know, does the aquatic nuisance species have access to the pathway? Does it arrive there? Yes or no? And once again, you can see there are corresponding probabilities of a yes or a no. Does the aquatic nuisance species pass through the pathway? Does it transit the pathway? Yes or no? Again, with corresponding probabilities. Once it passes through, does it colonize on the other side? Yes or no? And does it spread? Yes or no? We are interested in the top pathway in this event tree. So we are interested in an aquatic nuisance species that does arrive at the pathway, transits through the pathway, colonizes on the other side, and then spreads. And if we multiplied these 5 numbers together, we would get the overall estimate that the probability of establishment is 1%. But risk analysis is a framework for making decisions under conditions of uncertainty. So it's going to be important for you to handle the uncertainty that's relevant in your risk. And in this case, there's a great deal of uncertainty because there are things that we don't know about this unnamed aquatic nuisance species in this unnamed pathway. So please, as we proceed here, understand that these are hypothetical data. These are just made-up numbers to serve the purpose of a heuristic for this particular demonstration video. So, the probability of establishment is absolutely 100%. We're sure of that. There's no uncertainty because we can watch boats go up and down this pathway. When it comes to whether the species is ever going to get there in the next 50 years or so, here you see a very precise number. But what I want to show you that's actually in that cell is a fuzzier number here. In fact, we're using a probability distribution. Take a look at the number line. We're not going to get mathematical on you here, but this number line goes from 0 to 1. And what we're doing with this number line is representing our beliefs about what this value is. It's an uncertain value. And so to use a very specific number and to pretend that we have that kind of knowledge would be dishonest. So here we've basically said the probability that this aquatic nuisance species will arrive at the pathway is no less than 40%. It's no more than 80%. Now imagine the computer asking us questions. We've said it's between 40 and 80%, and the computer might say, do you know anything else? And in this case, we would say yes. 50% is the most likely value, and so if I raise that point up, I've got 3 points now, 40, 50, and 80%. These points are connected using a PERT distribution. We're not going to worry about those details right now, other than to say distributions are a topic that you will learn a great deal about in the certificate program. But let's take a look now at the probability that a species will transit the pathway once it arrives. Here you see a different shape. And I'm just using different shapes so that you understand this software gives you a great range of possibilities for representing your knowledge uncertainty and the natural variability in the world. In this case, we're saying the probability that it transits the pathway, it's no less than 10%, but it's no better than a 25% chance. When the computer asks us if we know anything else, this time our answer is no. That's why this distribution is shaped like a rectangle. It's basically saying any number in there, in that number line between 10 and 25% is as likely as any other. Now we move to the next block, which is representing the probability of colonization. Again, just to demonstrate the range of options, we show a triangular distribution here. It has a minimum probability of 1%. So there's no less than a 1% chance that there will be colonization, and there's no more than a 40% chance. Do you know anything else, the computer might ask? And we would answer yes. 10% is the most likely value. And so with these 3 points and a ruler, we can draw a triangular distribution. Just to close out the demonstration, let's take a look at the probability of spread. And this again is a uniform distribution with the made-up numbers for our example here of a minimum of an 81% chance of spread and a maximum 99% chance of spread. So what happens is each time we hit the recalculate button, the computer will reach into these distributions and randomly select a number and insert it into our model here. So you see the bright blue numbers, they're inputs, and they would change each time we recalculate the model. So I'm going to hit a recalculate just once and then we'll do a simulation. Notice in cell G1, the overall probability of establishment is 0.76%. And here is another iteration. This time with these values, it's 1.1%. So you could imagine that we might have many questions. Looking at the access to the pathway, we might say, well, what if that's 50%? What if it's 45%? What if it's 67%? And then we might be asking similar what-if questions for each of these nodes and branches in the model. And that would be quite tedious. So fortunately, the Monte Carlo simulation process enables us to run a simulation, which I'm going to do now. We're going to ask the computer to calculate this value 5,000 times, and what you see forming in front of you is a distribution of those 5,000 values. So a model like this enables us to be very honest with people, and if you were to say, what is the probability that this aquatic nuisance species will indeed become established, our most honest answer is we don't know. There's knowledge uncertainty, there's natural variability in the world, and for these reasons, this is a value that we can't possibly know yet because we have too many data gaps. Looking at the results here, if you look at the little spreadsheet column on the right, you see the minimum tells us that this probability of establishment of 5,000 calculations, the smallest one, was a 0.08% chance of establishment. The maximum was a 5.5% chance of establishment. So we've already bounded this number. And you see that number bounded in the distribution if you prefer the visual representation. The mean If you take all 5,000 estimates and sum them and then divide by 5,000, the mean is a 1.42% chance of establishment. So this is the way you do quantitative risk assessment. Just very briefly now, I'm going to switch to the consequence tab. When you see it, there will be no way for you to understand how it works. Don't worry about that. They're the types of details that you will learn and be able to do for those of you who would be interested in taking the certificate program. But I would like to at least show you the next piece of this. So take note of that value up there in cell G1, 1.1%, because that becomes the starting value over here, this 1.1%. And what we're doing in this is we're looking at a 100-year period. So right now, if you look in the center, you see a lot of zeros, all blue zeros. This is basically saying, in this static example that we're looking at, there is no establishment, there's no economic damage. The number that's of interest to us is this number right here. This would be the total damage over 100 years that could occur with different probabilities of establishment and different sequences of events and natural variability in the world. So once again, we're going to do a simulation. I'm going to be simulating the dollar damages here. So this distribution looks quite different. You see, in most years, there is going to be no damage at all. But in some years, there could be establishment of the aquatic nuisance species, and that could cause substantial amounts of economic damage. Once again, looking over at the spreadsheet on the far right, we have a minimum of 0 damage, a maximum of $234 million worth of economic damage. And that's what would happen if establishment occurred very early in those 100 years and we had close to 100 years of cumulative damage. The mean of these distributed damages that you're looking at is about $45 million. Now, once again, no expectation on my part that you really understand how this was done. This model's available to you in the course. Please feel free to take a look, those of you who have some understanding of how Excel models are built. Those of you who don't, our expectation is that in the course of this certificate program, that you would develop the skills necessary to begin to develop risk assessment models to this level of detail. So closing back, going back to our probability, once again, this is a simple example of a quantitative risk assessment.